Hello and welcome. Thank you for joining the preview of Lecture 1 of the ICONS 2026 Masterclass series on Advanced IC Design. My name is Boris Merman, and I will be talking about systematic design of sampling circuits in this course. So the significance of this topic is that sampling circuits are essentially everywhere where you have a continuous time input from the real world, let it be a transducer, some kind of antenna or cable, and you want to digitize that signal and thereby enter the discrete time domain and benefit from all the good features of digital signal processing and so on. So these circuits right at these interfaces are called sampling circuits, and they often present a very significant performance bottleneck in modern applications. This is very visible when you go to the latest conferences, for example, the ISSCC. Here I picked an example from a 12-bit, 12 gigasample per second pipeline ADC presented by Analog Devices. And you see at this interface, they employ a circuit that needs to meet very stringent linearity requirements in the 70 to 90 dB for relatively low frequencies. And then what you will always find is that these circuits deteriorate and become less linear for high frequency inputs. Here, 6 gigahertz yields a linearity around 55 dB. Similarly, if you go to the higher speeds, the distortion is even worse. So for example, in this case of an 8-bit converter that is meant to go up to 200 gigasamples per second, the linearity for low frequency inputs is only 50 decibels. And it made it deteriorate below 30 for very high frequency inputs, such as 47 gigahertz in this example. So what's the problem? What causes all these issues? Well, we can consider a simple example of an input that may contain some sort of a sinusoid, say with amplitude of 1 volt at 10 gigahertz. We can calculate the slope. The largest instantaneous slope of such a signal will be on the order of 63 millivolts per picoseconds. So that means if you just wait 1 picosecond, the signal is off again by 63 millivolts. And this is a number that's much larger than most least significant bits of any A to D interface. So this leads to a number of issues. The first one is that the resulting dynamic currents that you have to pump into capacitors that try to acquire these analog inputs can be very large. And here I have an example of a 5 picofarads capacitor. Based on this dV/dt, you would have to offer a 300 milliamp current to charge this capacitor in a timely manner. So this is very, very difficult. And whatever goes in this box will be very hard to design. That's, of course, only one challenge. The other challenge is simply defining the sampling instant to an accuracy that is much, much less than a picosecond in this case, and maybe 100 femtosecond, 50 femtoseconds or so, to stay within a very small deviation comparable to your least significant bits for this acquisition. So linearity and timing from this very simple example are obvious issues. So what we will do in this course is to study circuits that can help meet some of the latest requirements. And here's just one example, a bootstrap sampling circuit that basically is designed to achieve very high linearity in presence of high frequency inputs. And at the core of it is a main switch transistor, an NMOS device here that takes the input and tries to communicate that to a sampling capacitor carrying these large currents that we just talked about. And then to make this work really well, you have to build a lot of helper circuits around this. There may also be buffers in play and so on. And so in a way, this is a little bit like someone who gets a lot of help from the outside in sports who can barely hang in, but somehow survives because of the good circuitry that is provided around it. So we will look at this circuit and several others, and we will ask the questions of fundamental trade-offs and equations, how to even set the specifications to be achievable, what are some of the ranges to consider. And then ultimately, when we look at these circuits from the literature, how do we size all the components in a systematic way? Once we've done that, how do we simulate the circuit and fine-tune it, anticipate potential issues with layout parasitics and so on? And then lastly, from the simulations, how do we post-process the results? This is also sometimes non-trivial or not obvious to many people who are just getting started on the subject. So these are all topics that I will cover for different kinds of circuits, for different applications and different performance goals. So just to give you a snapshot on some of the outputs that are involved here. So we will build test benches that drive these simulations. So we can build a sampler and then put that in a test bench, observe the waveforms, send the waveforms out to a data file, and then ultimately use post-processing here done via Python to look at the spectrum, showing the distortion, and then looking at how the distortion degrades over frequency and so on. So one of the outputs of my course is that all the files that underlie these examples will be shared on GitHub, so you can reproduce them together with the open source circuit schematics that are used for these examples. So thank you again for listening, and I hope to see you in May to welcome you with my colleagues covering a variety of other topics in this class. Thank you. Bye-bye.